Christian can breathe a sigh of relief because I found a new cord yesterday. Not a new cord, another cord. So he doesn't have to come up here and hold it up. Okay. So, couple of announcements, and some of these I think you've heard before, just to remind you. If any of you are close to graduating, or know of someone close to graduating, if you're graduating this term, I hope your application is already in. If it's not, get it in today. Or as soon as you possibly can. Okay, and it's done online, so it should be pretty quick and easy to do. But if you're graduating in the spring, this is the very optimal time to start that process, okay? And it starts with a degree audit, is what they call it. You get your degree plan, the most current degree plan that you have, shows everything that you have taken, currently taking, and need to take. And then once you see that, you can determine if in spring term you can get everything taken that you need to take and graduate in the spring, okay? If not, get with your advisor and check out to see what you can do. And that's the second step, is get with your advisor. And then once the two of you are pretty much set on it, okay. Okay. Once y'all are agreed, then you apply online. Okay. It used to be the advisor signed it. Evidently online, we don't have to sign it anymore. So be sure you get your that process done. So even if you're not getting ready to graduate, you may know of someone who is, or sometime in the future, hopefully you will be graduating. Remember, the optimal time to apply to graduate is a term before you graduate. Okay? Term before. Now, there's a little bit of a bug in that ointment right now because we don't have the spring schedule ready yet. So it's not out there. You can't see if you can pick up all those courses you need. But hopefully these will be ready within a couple of weeks. And if they get it out there within a couple of weeks, then you can get online, see if you can get the courses you need. And if you can't, that's a good time to get in touch with the instructors or the department chairs or stuff and say, look, I need this to graduate. Is there any way you can offer this course this spring? Or is at a time that conflicts with the one other course I have to do? Is there any way we could work this out? You know, maybe change the time of one up before too many people get registered. And so as soon as you see that, that the schedule's out there, check and see if you can work things out. Usually we can. You know, I always will open a class if someone needs it to graduate. I don't know if everybody does that, but you know, so that's the process. And then you apply online. Now, two other small announcements. One is, and these could be pretty major too. Right, there is Skylar, right? Okay. All right. They were looking for, I assume they still are, note takers. If you would be willing to take notes for somebody who has some type of disability and are unable to take for themselves, they will pay you to do it, okay? A pretty good deal. You're helping someone else and you're getting paid to do it. So please consider that. Contact either Dr. Renee Herndon on this campus or the student specialist on the other campus. I can't remember her name right now, but check with Dr. Herndon here. She'll tell you, okay? The other thing, the Space Center was looking for tutors in math, English, Spanish, computer science, and I think biology, okay? So if you, I know y'all are good in math, but if you're good in any of the other subjects, you might want to consider tutoring for the Space Center. They will pay you, okay? And actually that's how you'll learn the material the best, is explaining it to somebody else, okay? So please consider that. Now, the other announcement is a little more personal, and it's an apology. I said we're working on the spring schedules because of all the changes they've done this year with all the labs and stuff like this, and they've changed even from what we did in the fall, this term, fall. These are a severe pain in the neck or some other anatomy. I don't know. But the deal is, I'm working on that. Well, this week, they said we had to have some sort of big thing in for SACs that had to be in this week. We have, I have to gather all the resumes from every instructor, full and part-time, and get those in this week. And we're supposed to be working on the spring and summer schedules this week. So I've had close to zero time to grade any paper whatsoever. So if you haven't seen a grade out there yet, it doesn't mean I haven't graded it. It's just I haven't been on Blackboard to put it in. Or, for a few people, I haven't graded it because they came in last time, 0 times since then. So I don't know if I'll catch up everything tomorrow. I'll try, okay? And I don't have a lot of opportunity tomorrow evening at home to do much. We've got a wedding to go to. And then over the weekend, if it continues raining, I may have time to get some grading done, okay? All right, good deal. Reggie, right? So, stand by. I think I told you early in the term, at the beginning of the term, there would come this time, about this point of the term, where I get really bogged down and things slow down. Yes? Anytime you're through with them, I'll take them. Okay? Good deal. Any questions? Okay? Thank you, sir. Oh, another. Good deal. Thank you. All right. And if you haven't realized it yet, we're nearing the end. Oh, there's another. Nearing the end of 1.8, and when we finish 1.9, we'll be ready for the test. So it's coming up pretty soon. All right, no questions? Here's where we left off last time. We had done example 5 and 6, and we formed compositions of 2 given functions. In calculus, it's also important to be able to identify 2 functions that make up a given composite function. If any of you have had any calculus or been exposed to it, there's a rule in taking derivatives called the chain rule. That's what uses composite functions, and that's why pre-calculus algebra introduces composite functions to you. Okay? For instance, the function h of x is equal to 3x minus 5 raised to the 3rd power. That's a composite function of these 2 functions. The cubing function, which is I call the outside function, and then the g of x, which is 3x minus 5, which is the inside function. So you have a function within a function, that is it. So, in order to decompose this function, h of x is 3x minus 5 to the 3rd power. That would be g of x raised to the 3rd power, because the 3x minus 5 is g of x raised to the 3rd power. The thing that raises things to the 3rd power is f of x. So it's f of g of x. Oh, you're already here. Okay. F of g of x, which you could, of course, have written. I'm almost surprised they didn't. Whoops, let me get my pen set up. Okay. They could have written this f circle g of x. So that's how we use the composite functions. Do we go back and do the F circle G's and stuff like that? Not really. We just use the concept in calculus. And we do the chain rule. And then later when we do integration, we have to sort of undo the chain rule. So again, you're always dealing with composite functions. Okay? So basically, to decompose a composite function, look for the inner function and the outer function, okay? The function h, the g of x, was the inner function. The x cubed, f of x, was the outer function. And then you always do outer of inner, okay? Always. Now, they're skipping example 7. So let's go back. I think that may be the best white space we have. Okay, that might be the best white space we have for doing example 7. Write the function h of x, which is equal to 1 over x minus 2 squared, okay, as a composition of two functions, okay? Now, before we begin, there's at least two different ways to write that as a composition of two functions. There's another way to write it as a composition of three functions. So you can take your choice. How would you write that as a composition of two functions? What would you say would be the inner function? X minus 2. What do you want to name that? You want any special name for it? They like g of x. Let's call g of x x minus 2, because I think that's what they're going to call it. Okay, what would be your outer function then? Absolutely. So that would be the outer function, which they like to call f of x is equal to 1 over x squared. Perfect. Okay? So writing that as a composition of two functions, if you name them this way, h of x would then be f of g of x, which would be f circle g of x. Now you don't have to write it both ways, just either way you'll do. Okay? Does that make sense? Can anyone see the other possibility? One way would be let your g of x be x minus 2 squared. And then your f of x would be 1 over x. That works. Okay? So there's usually, on some of these that are a little bit more complicated, there's usually more than one way to do it. Both of them are correct. Now, if you're doing WebAssign, which is perfectly fine to do, sometimes they'll say, nope, that's wrong, when it's really right, because they only recognize one correct answer, where this one has two. Another way to do it would be let g of x be x minus 2, let f of x be x squared, and then let e of x be 1 over x. That would be a way of composing three different functions: the reciprocal function, the squaring function, and x minus 2. Okay? So you could write it as a composition of three or more. Okay? Now, the book did it exactly the same way that you did. They did introduce something else, which when you get to calculus, I do all the time. Writing f of x as x to the minus 2 power. Frankly, in this problem, that makes it a little more complicated and maybe harder to see. The reason I always do it in calculus, if I was differentiating that or integrating that, I don't like having exponents of variables in the denominator. I want them as a negative exponent. Makes it much easier to take derivatives or to integrate. But this isn't calculus, it's pre-calculus. But that works too. All right, there is a checkpoint. Any questions on decomposing functions? Okay, there is a checkpoint bottom of the page. And yeah, I think composition of two functions would make sense on that one. But there's probably a couple of different, well, maybe just one way to do that. Now, before we get to the application, since we've been talking about decomposition of functions, I do have a dumb story. Do you want the dumb story or continue? Oh, dumb story. Wow, surprised. Okay. This spreads across different disciplines. But have any of you ever heard of Beethoven? Okay, I don't mean the big dog that had lots of puppies. Not that one. Okay. Oh, the musician. Yeah, okay, good. You've heard of the right one. Okay? All right. The Beethoven was, many people consider, and arguably, if not the best, one of the greatest writers of music of all time. I mean, incredible musical ability and musical mind. Okay? And coming in just for the dumb story is, yeah, I got it. I just got to find you. Yeah. There you are. Okay. So, one of the greatest writers of music of all time ever. Beethoven's Fifth Symphony is, I think, blows just about any other symphony completely out of the water. Dun-dun-dun-dun, dun-dun. You probably heard it in many contexts. An incredible piece of music. It broke all sorts of rules of its day, expanded rules of its day. It was just incredible. But even back then, when Beethoven lived, musical tastes were a lot like, hey, Ron's here. There you are. Unfortunately, people who like music were awfully similar to what they are today. Can anyone name the Grammy winner of 5 years ago? Probably not, okay? Because styles change, you know. Now, things change probably faster today than they used to. But after a while, hey, name please? Huh? Evan, got it. Kara, right? Kaya, okay. I just put you in the wrong place, okay? Okay. All right. So, unfortunately, musical tastes changed. They got tired of the big symphonies and the chamber music and that kind of stuff, even though it was really fantastic music. And they wanted other things. They wanted lighter things. They wanted different things. They wanted to hear things. And after a while, in his waning years, Beethoven had a hard time making it. There was no Social Security back then. It was probably always pretty tough being a musician anyway. But when he was at his prime, he could get the contracts or whatever he had to do. But after a while, people just weren't interested in that big music anymore. So as he got older, he also got poorer, okay? Unfortunately, that still happens some, but it was even worse back then. So, and on top of everything else, he was going deaf. And that's sort of a tough thing for a musician, okay? And what he did, he was really big on composing on the piano. I've heard this or read this before. He actually cut the legs off of his piano so it sat flat on the floor, and he sat on the floor cross-legged and composed there so he could feel the vibrations, and he was that good that he could sense vibrations from different notes or something. I couldn't even figure out when I was taking music which hand I was making a mistake in, much less, you know, feeling a vibration or anything. But he kept working, but he got poorer and poorer. And ultimately, and I think he was sort of a irascible old guy too. I mean, every picture I saw of him, he was, you know, he just didn't seem all that friendly and warm or anything else. So I don't know. But anyway, when he died a pauper. And I don't know if he had any family or if they were close. I don't know any of that. They buried him in what they called the potter's field, the pauper's tomb. You know, the landlady or whoever it was found them dead, you know, and she called, they came, drug him off dead. Well, as usually happens, and a few years later, people were feeling nostalgia and said, yeah, this music's okay, this new stuff, but you know, nothing really touched Beethoven. Whatever happened to Beethoven? You know, where is he? You know, they started looking around to see if they could see if he had done anything new. They found out he was dead. Well, where is he buried? He, you know, greatest musician of all time. You know, where is he buried? Out there in the potter's field. What? No, that will never do. We need to move him to a major cemetery and put up a nice mausoleum and commemorate this greatest musician of all time. So they had to go through all the paperwork to exhume the grave, move it and stuff, see if they could find family. It was a mess, but they finally did it. And they hired some people to go out there and dig him up, and they were lifting him. And from what I understand, he was a pretty big dude. I don't know if that was really true at the end, but every picture I saw, he seemed pretty substantive, okay? So anyway, they were lifting him out, and whoever it was did drop the casket, and the lid flew up. And there he sat with scores of sheet music, and he was just erasing like crazy. What was he doing? Decomposing. Okay. Never mind. Okay. That was my dumb story of the morning. Okay. Okay. We've had our decomposition of functions where we decompose what we did before. Let's move on to applications. Okay? Application. All right. Here is a more realistic, real-life type problem. The number of bacteria in a refrigerated food, and the way they phrase this is a little bizarre. What they mean by that, the number of bacteria in a refrigerated food depends on the temperature, and this is when you take it out of the fridge. You take it out of the fridge, and it starts warming up. That's when the temperature changes. Now these, temperature of the food is in degrees Celsius. So 2 degrees Celsius is right around maybe close to 35 Fahrenheit. 34 Fahrenheit. Close to that, not quite, but close. Okay? A little bit less than 34. Okay, but you bring it out and set it in the kitchen, and set it on the counter there, and leave it out for a while. Well, the temperature is going to rise. And what's normal room temperature of Celsius? Anyone know? Pretty close to 20 degrees Celsius. Okay? So 14 is getting close to room temperature. Well, the number of bacteria, okay, here's Ashley. She knew to wait till a little bit later to come in today because she knew I was going to do a dumb story. It's okay. So, smart move. Okay. All right. So, T is the temperature of the food in Celsius. So the food is warming up, getting closer to room temperature. As it does, because bacteria do not reproduce well at very cold temperatures. Okay? Around 2, they almost are at a standstill. Okay? But then when it starts warming up, they start reproducing sometimes like crazy. And this is the equation for it. They did this by doing many studies and doing regressions. This is what they came up with. 20t squared minus 80t plus 500. Now, try to get a little perspective on this. If t were 0, that would say there's still 500 bacteria in there. Well, t is never quite 0, so there probably is a few more than that at t equal 2. But anyway, here's the deal, folks. T2 less than t less than 14, that means this formula is no good for 0. So don't even bother with 0, okay? You would think you could use it, but you can't. The domain of this function is only 2 to 14. If it gets up to 20 degrees, that function's no good. It's probably they're reproducing like crazy then, okay? So this function is only good. The domain is only 2 to 14, okay? Well, that's degrees Celsius. Now, when the food is removed from the refrigeration, the temperature of the food is given by capital T, which is temperature in Celsius, of little t, time, given in hours. And that goes from, is 4t plus 2. That's the temperature rises at that rate, and that's only good from 0 to 3 hours. So in other words, you better not leave the food out there longer than 3 hours, or this function's no good, and they're probably reproducing a lot faster. Okay? So, let's just see what happens then. When t, the little t is 0, what's your temperature? 2 degrees, and that's where this one starts. So you see these fit together pretty well. And when your little t is 3, what's capital T? Anybody? When little t is 3, what's capital T? Say again? A little louder. 14. So you see, this fits that perfectly. The domain of this produces a range which fits the domain of that perfectly. Okay? So therefore, this was a great opportunity to use these composite functions. Okay? Now the question A, part of the question says, find the composition n composed with t, capital T, of little t, and interpret its meaning. Well, let's first do the first part. I don't have a lot of room here, so I'm going to have to write where I can. I think I'll start up here. What does n circle capital T of T mean. What's the definition of that? Composition of N with T of T. Hey, there's two T's here. Capital T is temperature, little t is time. What's the definition of that? What does that mean? Remember how we rewrote it? Oh, it was a long time ago, at least 10 minutes. 15? Okay. How do we write that? What does that mean? Like right here. This is going from this to that. Okay? It's just going backwards. What do we do this? Gave the big hint. Please, somebody help me. Okay? What does N composed with T of T mean? What did I say to remember? Think of the little O as meaning. Of. This will be N of T of T. That's your definition of composite function, right? Now, where do we begin? The inner or the outer? Inner, okay? And what's your T of T? So you leave the outer alone, N of, what's your capital T of little t? 4T plus 2. Perfect. Now, what does the capital N tell you to do to what's inside the parentheses? Say again? You start with coefficient 20, and then you do what with what's on the inside? Square it. And what's on the inside is 4T plus 2. And square it. Then what do you do? Minus 80 times 4T plus 2. And then plus 500. All right. Sorry, running out of room there. Yes?
What is that mixed up in the parentheses of 4T? Is that an 8?
Yeah, that's 80.
Oh, 80.
Yeah. Let me get around here. Let's see. Okay. The N composed with T, which is what they ask us to evaluate, N composed with T is defined to be N of T, okay? N of T of T. Start with the innermost function, N of, and what is T of T? 4T plus 2. So put that in there. Then the N function takes what's in the parentheses, which is now this, and starts with 20, and then multiplies it by what's in the parentheses, which is 4T plus 2 squared minus 80, that's what that was, times what's in the parentheses, 4T plus 2, and then add 500 to it as you're running off the page. Okay, so that's what we're doing there. Now, we got a little bit of work ahead of us, don't we? What's the first thing you got to do to that to simplify it? Okay, I'm going to try to write on this line here. I'm going to start over with the 20, and then we got to square 4T plus 2. How do we do that? You can FOIL it, and what would you FOIL? 4T plus 2 times 4T plus 2. That's what it means to square something. Multiply it by itself. And when you FOIL it, what do you get first? 16T squared. And then when you do the outer, you get plus 8T. The inner gives you another plus 8T, so that gives you 16T, little t, and then the last are plus 4. Okay? So there we've got the 20 times that mess. Okay? Now, what's next? I'm sorry? Okay. The 2T. Okay. What are you talking about?
Like right there in the parentheses, there's a 2T, I think.
Okay. Is this what you're talking about?
Yes.
Okay, that's the 20 from here.
Oh, it's a 20. Okay, never mind.
Yeah, it's a 20. She's making fun of my handwriting is what she's doing. Yeah, I'm not hurt by it much at all. It only hurts a little. Okay.
I'm sorry.
That's all right. I'm good over it. Okay. Never mind. What's next? We got the 20 times the 4t plus 2 squared. Then we got a negative 80 times 4 is negative 320 little t minus 160, right? Okay. And then you finally got a plus 500. Okay, see what I'm doing? I'm multiplying the 80 times 4 is minus, negative 80 times 4t is minus 320t, negative 80 times 2 is minus 160, and then the plus 500. Okay, still got to clear parentheses before we can do too much more. So let's clear those parentheses. 20 times 16t squared would be, help me. 320t squared. Is that right? Yay or nay? Okay. Plus 320t plus 80 minus 320t minus 160 and minus 500. All right. A good, whoa, say again? I didn't quite understand.
Plus 500.
Plus 500. Oh, I'm sorry. You're right. Okay. All right. Now it's a good time to start combining like terms. Do we have any other t squared terms? If you don't mind, I'm going to take out my smiley face foil here. Okay, we've already done that. If I could get it to erase. Okay. So that would be 320t squared. We don't have any others to compare with that. But what happens to my 320t's? Add to 0. Plus 320t minus 320t, they add to, yuck, 0. Okay? Now the constants. Okay? I have a plus 500 and a plus 80. That's 580. Subtract from that 160, and what do you get? 420. Okay? So it's a plus 420. Plus 420. Simplified sort of, didn't it? So that's what our n, I wish I had written this over. In fact, I think I will. Hold on just for a moment. Remember that 320t squared plus 420. Okay? This is what our n composed with capital T of t is. 320t squared plus 480? No, 420, wasn't it? Is that right? Okay. Whoa. All right. So we've done it. We've done the first part of A. Find the composition n of t. Now the second part, interpret its meaning in context. What does that mean? What was the capital N? Capital N was written right here. The number of bacteria, exactly, in a refrigerated food. Now, they gave it here as a function of temperature. What are they giving it now? As a function of time. So what we have here, up here, was the number of bacteria as the temperature is increasing. And then using the composite function of temperature with time, now we've got the number of bacteria as the time is increasing. The time that you've had it out of the refrigerator. Okay? So that gets you up there. Now we can look at this and say, when I first took it out of the refrigerator, T equals 0, how many bacteria were in it? 420. Okay? Guess what? There's bacteria in everything that you eat, probably. Okay? Probably a few in this candies there. Okay? If nowhere else, when you empty them out of the bag and file on the paper, they picked up a few bacteria. You can live with that. Your stomach has pretty strong stomach acids that kill a lot of those bacteria. Trees, got it. Thank you. Okay. Goodness gracious. There you are. Okay, got it. All right, good deal. All right. Anyone else come in, Sister Caldwell? Okay. So what we have here, we went from number of bacteria as a function of temperature, which is sort of hard to figure. You have to have a thermometer stuck in the food, to the number of bacteria as a function of time. And that, you can time it, oh, it's been 2 hours. Ooh, maybe we better put it back up, okay? Thanksgiving's a really bad time for this, right? You know, you're so sleepy from that turkey. Yeah, never mind. Okay. So, now, the B part here says find the time when the bacteria count will reach 2,000. It started off at 420. Find the time where it will reach 2,000. How in the world can we do that? Plug it in where? No, that's what we're looking for is a T. Say again? Yes, the N is equal to 2,000. So set this equal to your 2,000 because the number of bacteria is the 2,000. And now we'll solve for time. So what's the first thing we're going to do to solve that equation? Okay, we certainly can do that. Subtract, wait. Yeah, subtract 2,000 from 420. Is that what you were saying? Say yeah. Okay. You see why? Okay, because it is a quadratic, you want everything on one side and... Okay, well, you're probably going to take a square root, aren't you? Ultimately. Yeah, okay. Let's go on and do it the way, I'm going blank on your name, Cody, right? Okay, the way Cody was suggesting. Most of the time we don't do it that way, but this time I think it'd be legitimate to do it. Subtract the 420, is that what you said? From both sides. Okay. As long as all your moves are legal, you're okay. And that's legal, okay, in most states, okay? So this will be 320 t squared is equal to 1,580. Did I do my math right? Okay. Now what would you do? Say again? Divide by both sides by 320. Y'all are harder workers than I am, but that's okay. Okay, you got calculators. You can use them. Okay. And what does that give you? T squared is equal to? No. T squared is equal to? Second? 4.9 hours. Ooh, that sounds like too much, is it? 4.9. Yeah, that's... Something must be a little wrong with that. Let's see. What's that? Oh, yeah. Oh, okay. That's 4.9. Okay, 4.9. Just 4.9, not hours. Now what do we do? Square root. So T is equal to approximately 2.3 hours. Okay, now we're there. Now that makes more sense. Because you see, before, if that was that, you're outside the range, our domain. We're okay now. We're inside that domain. And how much is 0.3 hours? Anyone know? In minutes. Anyone? Pretty easy. 18. So about 2 hours and 18 minutes later. So that's approximately 2 hours, 18 minutes. You just take 0.3 of 60, okay? Because there's 60 minutes in an hour. So, it hasn't been out there the full 3 hours, but you've already got 2,000 bacteria living in that. Might want to put it up soon, okay? All right, your digestive tract does okay with a few bacteria, but when you overload it, some of them are going to get through, and then you could have the screaming meanies or something like that. Okay? We don't know what that is. Okay. Let's move on. Any questions on that? All right. Here's how they did it. The N of T is defined as N of T, okay? And then we plug in where we had the little t, capital T was 4t plus 2. Everywhere we saw the little t, the capital T in the original problem, and plug that in, and that gives us 20 times 16 squared plus 16t squared plus 16t plus 4 minus 320t minus 160 plus 500. And when you work that out, that's 320t squared plus 320t plus 80 minus 320t minus 160 minus plus 500. Just like we did. Y'all got it perfectly right. And then that resolves to be 320t squared plus 420. Now, I said y'all worked harder than I did. At that point, I would have divided out at least 20, okay? And that would have left me 6t squared plus 221 or something like that. Those are much easier numbers than this way. But you did it correctly. Everything was fine. You have calculators. You could use them. Okay. But you didn't have to yet. The composite function, N of T, represents the number of bacteria in the food as a function of the time since it's been out of the refrigeration rather than the temperature that it was at. Okay? Now this is where I meant I would do it. Okay, sorry, I got ahead of myself. Once I had this equation here, that's where I would have divided by 20 and would have had, what did I say, 16t squared plus 21 is equal to 100 or something like that, just to get the numbers smaller. But they didn't mess with it. They just said this is the answer. They said 2.2 hours. I don't know how they got that, but probably was pretty close. Okay, that would be 2 hours and 12 minutes. We said 2 hours and 18. Sometime in that time frame, you reach 2,000 bacteria, which is not good, probably. Okay. Now, on top of everything else, your whole digestive system is filled with bacteria. Most of them beneficial, good stuff, okay? It's just a few of them aren't so good, and if you get those in there, they can mess up everything. And generally, out of food, they're not going to be the good stuff. Okay. One exception to that usually is yogurt. Yogurt contains certain bacteria. You'll see those big old long names on the yogurt containers, and those are usually very beneficial for your digestive tract. I think the term for them are the biotics or whatever, healthy stuff that way. There is a checkpoint there if you have unless someone wants it done now, a good thing to do shortly after you leave class. I think that's the last slide. Nope, but note that when you solve the equation, you reject the negative value. Oh yeah, I forgot to say that. When you take a square root, it's always plus or minus. A time of negative 2.2 hours doesn't make a lot of sense. That means before you took it out of the fridge, 2.2 hours, no, that makes no sense at all. You didn't have 2,000 bacteria in it then, so that makes no sense. So you rejected that. I should have done that when we were doing it, but we were so crowded on the page. Okay. See, right back here, when you took the square root here, anytime you take the square root, it should be plus or minus. But in this case, that makes no sense. So we correctly ignored it. Okay. And the other reason, the negative value wasn't in the domain anyway, was it? It was 0 to 3 hours. So yeah, out of the domain, forget it. Oh, and that's the end. Okay. Homework, well, that's before we go to homework exercises. Two functions, f and g, this is vocabulary, top of page 81. Two functions, f and g, can be combined by the arithmetic operations of blank, 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 and blank. What do you, second? Sum, difference, product and quotient, or addition, subtraction, multiplication, division. Both of those are great answers. Okay? Number 2, the blank of a function f with another function g is f circle g of x, which is defined to be f of g of x. What is that blank? Composition of functions. Okay. And why they don't have one about decomposition, I don't know. Okay. So, homework exercises here. Number 3. Okay. It's at calcchat.com, so you can follow it there if you can't do it. Then, any of the odds 5 through 11, they're all at CalcChat. 11 is at CalcView. Then do any of the odds, any of the odds 13 to 23, they're all at CalcChat, 13's at CalcView. Then do either 25 or 27, they're both at CalcChat, 25's at CalcView. Do any of the odds 29 to 33, they're all at CalcChat, 33's at CalcView. Do any of the odds 35 to 41, they're all at CalcChat, 35's at CalcView. Do 43, the only one like that, that's at CalcChat. Either 45 or 47 or both, they're both at CalcChat, 45's at CalcView. Any of the odds 49 to 55, they're all at CalcChat, 49's at CalcView. And then do any of the odds 57 through 63. They're all at CalcChat. Okay? And Ryan is here, right? Okay. I've already marked you here once by mistake, so I got you correctly this time. Okay. I was psychic. Okay. So, any of the odds, 57 to 63, they're all at CalcChat. There is a true-false, number 65. It should be at CalcChat as well. There's number 67, I think you can do. That should be at CalcChat. There's a proof at 69. If you're into proofs, go for it. Math majors love proofs, right? So do that if you'd like. 71 is a writing function. You can do that if you choose. Another proof at 73. Any questions? That finishes 1.8. So let's move on to 1.9. Okay. All right. There we are. Now, this is the last section in Chapter 1 that we're going to do. So when we finish this one, we'll be ready for the test, which I'm guessing we'll get it started today, hopefully finish it on Tuesday. So we could have the test as early as Thursday of next week, 1 week from today, or possibly Tuesday of the following week. Okay? All right. Cheers. And yes, okay, I heard. Okay. Okay. Let's go from current slide. And we're still in Chapter 1, which is functions and their graphs. And as you noted, this author loves graphs. Now we're going to talk about inverse functions. Before we talk about that, we have to introduce a few other issues here. Okay? One objective is to find inverse functions informally, which I think is almost a waste of time, but we're going to do it because they do it in the book, and verify two functions or inverse functions of each other. That's not a waste of time, so we'll do that for sure. Use the graphs of functions to determine whether functions have inverse functions. Yeah, that's okay, but graphing is sort of a pain in the neck too. And then, on the basis of graphing, we'll introduce a new test, the horizontal line test, to determine whether functions are one-to-one. That's a whole new concept there. So we will define what it means to be one-to-one. And then we'll learn to find inverse functions algebraically, which makes a lot more sense than doing it, what do they call it, informally, okay? Doing it algebraically basically removes a lot of error, okay? So we'll do it algebraically, which is always fun, right? That's the good stuff, algebra. All right, let's first talk about what in the world an inverse function is. Now, several ways to express a function. Remember, you can express it as a graph, you can express it in words, you can express it as an equation, or you can express it as a series of ordered pairs, okay? Set of ordered pairs. Now, most continuous functions, they're really a pain in the neck to do as ordered pairs because you can never write them all, okay? But we can refine our domain and then write them as ordered pairs, okay? So, here's a function, really simple function. F of x is x plus 4, right? Now, this function x plus 4 would be a great continuous function, but we're going to find it only on set A, whose values are 1, 2, 3, and 4. What would be the values of the range? Set B. If the inputs are 1, 2, 3, 4, what are your outputs? Put in a 1, what do you get out? 5. Next. 6. 7. And 8. Okay, we got it. So there's our output function. So there is, now we can, if this is all our domain, that's all the range, and it can be written as this function, x plus 4, which you could write as a set of 1, 5, 1, 5, 2, 6, 3, 7, and 4, 8. Because those are the ordered pairs that go together. You can't just mix them up. Those are the ordered pairs that this function describes. Right? Now, in this case, what happens if you interchange the two values? Okay? If you write some new function, 5, 1, 6, 2, 7, 3, and 8, 4. If you exchange those two values, you've now denoted a new function which we call the inverse function. Okay? And that is denoted by f to the minus 1. Now, time out a moment here. They're going to talk about this later, but I think it's important to talk about it now. Give me a number, any number.
10.
Second?
10.
10. Okay? If I had 10 to the minus 1, what does that mean? 1/10. That means 1 over 10. Give me a letter, any letter. Okay? A. Okay? And if I said that to the minus 1, what would that mean? 1 over A. Okay? Okay. Algebraically, raising something to the minus 1 power is the reciprocal. That's a reciprocal function. Okay? But if you're doing a function, that is not 1 over f. Not 1 over f. F to the minus 1 means inverse function of, not 1 over f. Please do not confuse those. Okay? Okay, that new inverse function is a function that now maps from B to A, rather than mapping from A to B. And it can be written as follows. Okay? How would you get these values? In every case, how you start with the first one and get the second. You subtract 4 from it. So there is your inverse function of f, which was x plus 4. Okay? So if x plus 4 is your function, f minus 4 is its inverse. It takes exactly the same range and makes it the domain of exactly the same range, which was the domain of the first function. Okay. Note that the domain of f is equal to the range of f inverse. The domain of f was 1, 2, 3, 4, remember? Now that's the range of f inverse, 1, 2, 3, 4. Okay. And vice versa. What was the range of f, 5, 6, 7, 8, is now the domain of f inverse. Okay? Now, here's what we mean on the mapping diagram. This is another way you can represent functions. This is the domain of f, your x, okay? And you operate on f with this function here. You get a range over here. This was 1, 2, 3, 4, and that produced 5, 6, 7, 8 over here. Now, they're not always going to be that nice of numbers, but it is in this case. But then, if you take those values and make those the domain of f inverse and map it back, you get exactly the same x's you had to begin with. 1, 2, 3, and 4. Because f inverse subtracted 4 from each of those values, where f is added 4 to each of these values. Okay? Now, guess what? You've been dealing with inverses your whole life in math. Because what's the first operation you learned? Well, maybe the first one you used was counting. But after you learned to count, what was the first operation you learned? Second? Addition, of course. And you worked so hard at memorizing all those math and flashcards and all whatever they did back at your day. Okay? And when you finally thought, hey, I've got math under control, then they turned around and did what? Made you subtract. Well, and then when you subtract, you undid the addition, right? You were doing an inverse operation, they never even used the word. And then they taught you to multiply, and you had a whole new set of flashcards and things to learn. And then once you finally got those under control, what they have you do? Divide, which undid multiplication, so you were there doing inverses all along. Okay? And then much later, you raised things to powers, didn't you? This is several grades later. And then, a little while later, you did what? I couldn't hear it. Oh, yeah, we haven't gotten there yet. But once you raised things to powers, how did you undo that? Taking roots. Inverse functions. Okay? So, you've been doing it already. Now we're formalizing it a little bit. Make sense? Okay. In other words, when you write the composition, oh, man, we're back on compositions again. The composition of f with f inverse, or the composition of f inverse with f, you should get something that's sort of interesting. Let's do that, okay? I'm going to try to get up here and cover it before you look at it too much, okay? Let's do the function of f. What was our f inverse that we just had? X minus 4. So f of x minus 4, what did f tell you to do? Remember what f was? X plus 4. So it said take whatever's in parentheses, it was x, and add 4 to it. Now you take x minus 4 and add 4 to it, right? And that gives you x. Let's do the inverse. Now remember, usually when you compose two functions, f and g, and then do g and f, they usually don't come out doing the same thing, right? Most of the time they don't. But in special cases, that's pretty important. If you do f inverse of f, what was f? X plus 4. So f inverse of x plus 4. But what does f inverse have you do? Subtract 4 from whatever's inside the parentheses. So it's x plus 4 minus 4. And guess what that comes out to? X. In this case, the composition is commutative. Most cases it's not. This case it is. And not only is it commutative, it always gives you the same answer. And why is that? Because what you chose as your input of f, say on the second one, when you operated on that, you got an output, and then the f inverse took the output and went back to the input, so you wound up with the same x you had to start with. That's what an inverse function does. And that's how you tell whether you have an inverse function or not. Excuse me. Okay? Now they're doing it informally. If you had the function f of x equal to x squared, 4x, sorry, 4x, do you think that has an inverse? And if you think it does, what might that inverse be? What would be your first guess? If the function is 4x, what would be your first guess? Yes. Okay. We had a suggestion of negative 4x. Okay. Let's check it and see if those are indeed inverse functions of each other. So let's first do f of f inverse, and then we'll do f inverse of f. Sorry. Okay. So what is f of f inverse? If indeed f inverse is negative 4x, that would be f. Whoa, goodness, I should get back here. Okay. Ah, good, here we are. F inverse, this would be F inverse we're suggesting is minus 4x, right? And what does F tell us to do? Take what's in the parentheses, which is minus 4x, and multiply it by 4, right? What does that give you? 4 times minus 4x. Question, is that equal to x? No. So that's probably not the inverse. So I'm not even going to mess with the second one, okay? So let's do another guess. This is why I don't like informal, okay? It's pretty unprecise. I'll put it that way. Let me get my, whoops, wrong thing, sorry. Go back. Okay, this is the one. Okay. Anyone make another guess? X over 4, okay? Now, he's doing what was suggested earlier, the inverse operation of multiplication, which that one is division. So, here's a suggestion of x over 4. Let's see if the same things work. Let's do f of f inverse of x, and we'll later do f inverse of f of x, okay? Now, what you do first, the inner or the outer? Say again? Inner. Okay, so it'll be f of, and what's your f inverse? Say again? X over 4. And what does f tell you to do? Multiply 4 by whatever's in the parentheses. So that would be 4 times x over 4. And that would give you x. All right, we're halfway there. That worked. Let's do it the other way. F inverse of f. You do the inner first. F inverse of. And what's your f? 4x. And what does f inverse tell you to do? Divide what's in parentheses, 4x, by 4. And what does that give you? X again. We got it. Okay? We got it. Okay? Verify that both f of f inverse and f of f inverse of f are equal to the identity function, which is x. Okay? Make sense? Excuse me. Okay. I'm going to erase what I did. Y'all need it a little longer. We're going to see it with what they did. Okay? Or do. Okay. F, since the function f multiplies each input by 4, to undo that, we'll try to divide each input by 4. Okay? So that's why the second choice seemed to work better. F inverse, we're going to suggest informally to be x over 4. And therefore, to verify this, f of f inverse would be f of x over 4. But the f function says, take whatever's in parentheses, multiply 4 by it, 4 times x over 4, sure enough, is x. Okay? But to do it the other way, f inverse of f is 4x, and f inverse, say whatever in parentheses, divide by 4. And that gives us 4x divided by 4, which is, again, x. We got it. Those are inverse functions of each other. Make sense? All right, good deal. Now, here's the definition of inverse functions. Let f and g be two functions such that f of g of x is x for every x in the domain of g, and g of f of x is x for every x in the domain of f. Now notice here, they may be different x's, okay? But they still come out being x, okay? Under these conditions, the function g is the inverse function of the function f, and g is denoted by f inverse, okay? So f of f inverse is always equal to x, and f inverse of f also has to be equal to x. The domain of f must equal the range of f inverse. The range of f must be equal to the domain of f inverse. Those very things we saw from the very beginning. Make sense? Okay. Anyone still writing? Okay. Now, here's what I said before, and they're saying it now. Do not be confused by the use of the -1 as a superscript to denote the inverse function F inverse. In this text, whenever you have a function raised to the -1, that always refers to the inverse function, never to the reciprocal, ever. A variable to the -1 is reciprocal. A number to the -1 is the reciprocal. A function to the -1 is the inverse. Okay? If the function g is the inverse of the function f, then automatically you know f is the inverse of g, because these are unique functions. Once you find one inverse, that's the only inverse you'll ever find. And it goes the other way. For that reason, you can say that the functions f and g are inverses of each other. Okay? Excuse me. Okay. Now, they skip example 2. Do we have time for example 2? Yes? Yeah, I think we do. So let's go back and see if we can do example 2. Oops, right here. All right. Which of the following functions is the inverse function of f of x? Here's f of x, and that's equal to 5 over x minus 2. Okay? Well, one choice will be g, and g of x is x minus 2 over 5. And the other choice would be h, and h of x would be 5 over x plus 2. Anyone want to make a vote on which one of those is the inverse of f? G or H? Or no opinion? Okay. In the elections, you better vote. Don't have no opinion. Okay? Never have no opinion in a real election. This one, it's okay. How do we check to see? Well, we do our test. F composed with G of x. Okay, and what would that be? Do the innermost first. What is your G of x? X minus 2 over 5. And what does F tell you to do with that? Start with 5, and then divide that by whatever's in the parentheses, which is x minus 2 over 5, and then subtract 2 from that. Okay? Does it look like there's much hope in that? That's going to be a mess. Now, here's how I deal with a mess like that. This is, some books call that a complex fraction. I don't like using the word complex, so that usually means you got the number, imaginary number I in it. This doesn't. I call it a complicated fraction, when you might say all fractions are complicated. No, they're not. Okay. So what I would do was take the common denominator from all your denominators. The only denominator you have is 5. Multiply numerator and denominator by 5. That would make a 25 on top, and x minus 2 minus 10 on the bottom. So that's 25 on the top, and a x minus 2 minus 10 on the bottom. That would be a 25 over x minus 12. You think there's any way you're going to get an x out of there? No. Hang it up, Jack. Yes.
So 5 over x minus 2 over 5 minus 2, that second function, is that inverse of g of x?
No, it is not. Oh, this one down here? Yes, it is. This one here? No, it's not. Oh, back here? No. This is trying to see if it is. It's not going to work. Not going to work. I sort of hate it when they give you things that don't work. Okay? Let's try the other one quickly. Okay? I'm going to erase some of what I've done here. Okay, we'll see if we can make this work. Okay? Now we're going to try f of h of x. And that would be f of 5 over x plus 2. Okay? Now what does your f function tell you to do with that? help me, 5 over, and instead of what's in parentheses, we put that first in the denominator, which is 5 over x plus 2. Okay? And then subtract 2 from that. That's what the F function tells you to do. Excuse me. Okay. All right. What would you do first down here? Excuse me. What do you do first? 2 minus 2 is 0. And then you got 5 over x. Well, that's the same as 5 divided by 5 over x. And how do you do that? How do you divide fractional forms? Invert and multiply. Times x over 5. Yes. I'm sorry?
Why you put the minus 2 in the denominator?
Okay. Good question. All right. What we're testing here to see if h of x is the inverse of f, right? So this is the h of x. So I put this in here, right? Now what does the F function tell me to do? Start with the number 5. So I started with 5. Put it all over whatever is in the parentheses here. What's in the parentheses here is x. What's in the parentheses here is 5 over x plus 2. So I put that there and then subtract 2 from it. You see this? That is where the minus 2 came from. It's whatever's in the parentheses here, which is that, minus 2. You see it? You see it? Okay. And that's where it's at, and that's then the 2's go out, and you flip it over. Yeah, you wind up with that. You should really do it the other way. We just don't have time, so we'll have to live with it that way. All right, let me give you a few homework exercises here. We kind of finished example 2. Please do the checkpoint for example 2. We'll start next time with the graph of inverse functions, which is the top of the page on page 86. Let me give you a few homework exercises. Okay. They would be any of the odds 7 through 13. They're all at Calc Chat. 9's at Calc View. Either 15 or 17. They're both at Calc Chat. 15's at Calc View, and we'll do the rest of those next time.
Do you have a staple?
Not in here. I have it in the other classroom. I'll try to keep them together. Okay?
My name is?
Huh? Yeah, the name's on. Okay.
I didn't know if you were going to think I had paper or not. So I just wanted to know.
Yeah, that's fine. That's fine. Yeah. Okay. Good deal. Now remember, folks, I'm behind in grading now, and I've got to get a bunch of resumes put together and fall and spring and summer schedules done before I can get back to my regular grading. So don't expect these super soon, but I'll try to have them ready for you next week, best I can. Good deal.